system. So the term fraction is now being used more to describe the same process. But the point is that when you divert water into an irrigation system through a canal system, there are losses along the way, quote unquote. But this water doesn't mean that it can't be reused again in other parts of the system. Okay? And that's what I'm going to try and point out today. Another term that you will listen to, or you hear if you read the irrigation literature, is the term consumptive use of water and non-consumptive use of water. Okay, so basically what that means, consumptive use is when water, for example, changes state from vapor form in the form of evapotranspiration, and that can be from weeds and phreatophytes in the canal and drain systems along the rivers. It can be from evaporation from reservoirs and canal water surface. And it can mean deep percolation that becomes unusable because it picks up salts, for example, or the water quality is degraded to a point where you can't economically use that water any longer. And then non-consumptive losses are things that go on every day in canal and irrigation system, which is seepage to the groundwater system, deep percolation from the field into the groundwater system, surface runoff from the fields and tailwater losses from the canals. Those usually go back to the stream. And operational spills, meaning in order to avoid overtopping of the canal, there's outlets that allow the water to spill into a drain and go back to the river system. So these bottom are non-consumptive losses, because even though the water was in the irrigation system, it's going to make its way back. So, for example, storage efficiency. Well, what makes the amount of water released from a reservoir less than the amount diverted into it? Well, that would be deep percolation or seepage from the reservoir bottom. Okay, that water could be going around the dam into the river system again, and then the losses from evaporation from the water. From the water surface. Okay. Typical canal system, you would have the inflow or headworks, which are diverting water maybe directly from the reservoir or from a river just downstream from a reservoir, and the water then travels through many pathways into the, and there will be inputs and outputs to that canal system. You can have seepage moving in to the canal. You can have seepage moving out of the canal if it's an unlined earthen canal, for example, as opposed to a lined concrete canal. You have some that can flow into the canals. This is very common. Logan, where the city and the canal companies allow the city to dump some of their stormwater into the system, and that goes that would be a runoff inflow into the canal system. The water then travels into the lateral canals and gets distributed into the fields for irrigation, and then some of that water could spill at the end of the canal due to an operational problem. And so, as I mentioned, instead of allowing the canal to overtop, you spill that water into a drain, and it gets back into the river and so forth. So these are the multiple pathways of water in a typical canal system. And when you hear the term conveyance efficiency, that's the ability of the canal system to deliver water without quote-unquote losses. For example, it's the water diverted, for example, into this lateral, divided by the water that was diverted into the canal. So it's the water that's diverted here, let's say all the water is diverted here, and if you divide by the amount of water that went in here, you would have a measure of how much loss was in the system. But the difference could be because there's seepage, for example, going into the groundwater. Doesn't mean that it's lost. That usually is connected to the river hydraulically, where the water came from in the first place. And then at the field level as well. At the field level, a typical irrigation would be, say here, applied, and some of it gets infiltrated. Some of that infiltration goes beyond the bottom of the root zone of the crops, and is the process we call deep percolation. That water then goes into the water table. Some of the water gets evaporated from the soil surface, and some of it is transpired by the plants. The combined evaporation and transpiration is what you've all heard about, ET, evapotranspiration. Now, irrigation, what we're interested in is depositing the water in this layer, okay, in the root zone, because then it's available for plants to use. If the water goes beyond the root zone, it's not available, okay? It goes into the groundwater system. Now, that groundwater, again, could be pumped, and most of the time it's connected to the river system and ends up there over a longer time span. Some of the waters are run out from the field, and they can go directly back into drains and into time scale. So what we call application efficiency of a typical field or irrigation means that it ends up in the root zone divided by the total amount of water applied. Okay? The difference is the stuff that's running off and the stuff that's deep percolating, and some of it evaporating from the soil surface. So you hear about efficiency of systems, right? Furrow irrigation and surface irrigation is usually efficiency, okay? Anywhere from 25 to 65%. It depends on many factors, on whether the field is at the vis-a-vis the infiltration characteristics of that soil. Okay, sandy soils have clay soils, surface irrigation. Okay. Then you have on the other end subsurface drip systems, where the water is delivered at the root zone of the crop, okay, and avoiding evaporation and deep percolation and so forth. The reason the surface irrigation systems have more quote-unquote losses, meaning deep percolation or runoff, is because you have to apply a larger slug of water, okay, to get that water to the end of the furrows or the end of the field so that it can infiltrate into that root zone. And usually you have to apply a lot more water than if you were applying directly into the root zone of the crop by a trickle irrigation system. Okay? So those are a big differences there. Now, of course, you can have systems like sprinklers which have a higher inherent efficiency, but of course, any is not going to be doing what it's supposed to do. So here you see, this sprinkler putting out 7 gallons per minute, and then the leak right beside it is putting out another 5 to 10, right? So here, they're being inefficient more efficiently, if you allow me to do that, right? So again, the management of the system is key to ultimately attaining some of these percentages that you see here. So I've listed for increasing efficiencies, but I'm not going through all of these. I'm just putting it in the presentation for completeness. And later on, this is going to be available for people to look at. But anything from increasing water quality, saving water, increasing pumping or energy, and so forth, all those are increasing the efficiencies. Then there's a lot of things that can be done on farm. Usually, if you have a poor designed you can use land leveling to slope of the field more with the infiltration properties of that soil. That's done a lot in Southern California, for example. The Palo Verde irrigation district valley, some of these large irrigation to try and improve the application of water, even though it's surface irrigation. And so there's other ways of improving is to do irrigation scheduling, which is a technique on estimating how much water the crop is using through ET, and then irrigating and delivering just the right amount to replenish that water. Okay? Of course, you have to add the inefficiencies of the system, like I mentioned. Even if you add just the amount to replenish the water in a surface irrigation system, your water might not reach at the end of the field. Okay? So you usually have to apply more water to fill that root zone. Okay? And there's other techniques in surface irrigation that can lead to improvements in the application of efficiency. You can collect the tailwater and reapply. That's done in Southern California as well. You'll see them collecting the water that's running off the field into a ditch, and then they up to the top and mix. Not leaving the system. And I've put a table that sort of summarizes all these processes that I just mentioned. And then key word over here that you'll hear also, that you read about in the irrigation literature, is beneficial use of water. And that comes down to water rights. Okay? And water rights is going to be part of our discussion later on, I'm sure, at the end of this talk. It's the water rights system in the West that, on the one hand, allows buying and sell and so forth, but it also leads to these in the system which some people argue is a problem. Uses of water and non-beneficial uses of water, and you have consumptive uses and non-consumptive uses. And again, non-consumptive use, the water is available to be used again, except when its water quality changes to a point where it's not economically viable to do so. Well, we have a case right here on the Bear River system. Okay, once that water goes past the Bear River Bird Refuge, it's in the salt sink. It's in the Great Salt Lake. Okay, and then unless our colleagues down at the University of Utah really get a grasp of cold fusion and energy to recover that water, it's quite a costly deal, right? A reverse osmosis. It's doable, but it's expensive. So I'm going to give system so we can look at where the water is going. This is a study area in Southern California, the Palo Verde Irrigation District, about 500 square kilometers. Alfalfa, cotton, grains, and melons, and some other small vegetables are the main crops. By far, alfalfa and cotton are the big ones. Alluvial soils and an arid desert climate. What we're studying here, and this is what part of Saleh's PhD research is, we're trying to close the water budget on that system, okay? And that system, along with the riparian zone, beside it as well. And the reason the Bureau of Reclamation, who is funding us, is interested in this is because they would like to divert or release water from the big reservoirs upstream on the Colorado River system. They want to get it, they just want to release enough for the irrigation of the different systems downstream from, let's say, Lake Mead, right? And enough to supply the riparian vegetation. Fisheries, if there's a fisheries habitat problem, which is not the case on the Colorado River. And then whatever's left over goes into Mexico. They don't want to give any more water than the treaty calls for. So it's a problem, and they look at methods of improving the water balance. So this is a very simplified water balance. You have the inputs from precip and river diversions, in this case into the main canal, and then the output, which is the canal spills and the drains, the main drain down there, the output of ET, which is really the consumptive use. Okay, this is the ET is the true loss of water in the system. Okay, because it's gone once it transpires, it's gone. Okay, and then of course changes in storage. Okay, so to estimate ET, we're using a remote sensing technique. This is a Landsat image which contains the Palo Verde Irrigation District. Zoomed in, this is the city of Blythe on I-40, I believe, right? I-40. It goes from Phoenix to somewhere in California. I-20, I don't remember which I it is. But we're using a couple of models, but I'll just show the results for SEABAL, the Surface Energy Balance algorithm for land that was developed by Wim Bastenson in the Netherlands. And here we use remote sensing to estimate the net radiation, the sensible heat flux, the soil heat flux, and by rearranging this equation, we obtain the latent heat flux, which is the evapotranspiration. Okay? this model is programmed up in ERDAS Imagine, and there's an iterative component to it, but you got to run separately in a spreadsheet. The Mono-Nabokov stability corrections, all that. Then finally, instantaneous latent heat flux map, right, for the instant of the satellite overpass, pretty much an instant in time. Okay? We divide that by the reference ET from a weather station within the irrigated area. Okay, so CIMMYS, the California network of weather stations, automated. There's like 3 or 4 of them, and we're using data from a couple of them. And we get then the reference evapotranspiration from the Penman-Monteith at that same half an hour or hour period that the satellite came over. And we divide the instantaneous values of ET from the satellite technique by the reference ET, and we get a fraction. Actually similar to a crop coefficient in this context. And then we multiply that fraction by the total ET from the weather station. And the total ET on each one of those throughout the whole Palo Verde irrigation district. Okay? And that gives us what the approximate demand for water is on that particular day. We sum everything up. Okay? Now, if we do that for several satellite images, here is satellite images, 20 dates throughout the whole year of 2008. We can now look at a sort of a demand hydrograph due to evapotranspiration, okay, which is one of the big components of the water balance. Okay? Let's look at some of the others, inputs. The precipitation. Here we have several gauges, and this is an arid area. Okay? So precip is not a big significant component to account, because when there is some monsoon rains in the middle of the summer, they do cut back on the irrigation deliveries. Okay? So that is something that the Palo Verde Irrigation District does do. So we've looked at the precip as an input, and then the surface inflow, which is the diversion dam at Palo Verde, where the water gets diverted from the Colorado River into the main canal. Okay, that is over here on this top portion. And in blue, you see the whole network. In red, you'll see the network of drains. Okay, this was painstakingly digitized by Saleh. And of course, the Palo Verde Irrigation District is thrilled to have this type of digital data, and they're using these products now. But by along the system, there's water measurements, like at the main input, and then in each one of these end of these canals, there's spills. Okay, so instead of overtopping, the water spills over back into the river. They're measuring that water as well. Everything that's being spilled is being measured along spill points. And then the drain is collecting all the spills runoff from the surface irrigation. Not all fields are running off, but some of them are, though. That water that runs off goes directly into the drain, and then the drain is also collecting subsurface groundwater from that deep percolation process that's going on in each field. Okay? And that's all being measured down at the outlet, okay, by gauges as well. So we have all the measurements of input and output to the system. Okay? And you see the hydrograph here on the right is the inflow Okay, so as you would expect, the inflow, the peak diversion occurs in July, the hottest time of the year, okay, when a lot of irrigations are going on more frequently, okay, and the demand for irrigation water is the greatest. And then it's lowest in the winter months when not all fields are producing. There may be some vegetable crops and so forth. And even the alfalfa is using a lot less water from ET. So that's the inflow hydrograph. This is the outflow hydrograph, which is a combination of the drain, the outlet drain, and all the spills that go along here. And the spills are a small amount compared to the drain outflow. Okay, on the left you have precip and the inflow from the diversion, and we have USBR and USGS because both agencies have gauges, okay, at the inflow, at the outflow, and so we were trying to see if there was any problems, one being more accurate than the other, and they've used slightly different techniques on how they measure flow. And on the right we have the outflows from the drain and then with the actual ET, okay, overlaid on top of it, summed to it, and that's from the Seaball estimates of evapotranspiration, okay, from the remote sensing. So I could see matches approximately that one, which is what it's supposed to do. Okay. Now let's look at the closure. So this Saleh supplied me with this, and he's done all these calculations. And here he's trying to close on a daily basis, and then here on a weekly basis, on a monthly basis. But on these three graphs, we really haven't taken into account the storage term, okay? Meaning that deep water that's deep percolating beyond the root zone of the crops, that's going down into the groundwater, that's being stored there. Groundwater is going up, the level's going up, and it's going down throughout the year. Okay, so when we close it on a yearly basis, and I'll show you in a minute why this is okay, we're pretty much saying that we assume that the groundwater on a yearly basis is coming back to the same point as it did when we started, okay? And when we look at the yearly basis, our closure is within 2%, okay, which is pretty good, okay? Meaning we're accounting for most of the water in our area is about 2%. It's pretty good. But let's look at the groundwater, okay, because it's okay? And it's again, and I'm trying to make the point here that this water is not lost, okay? And so luckily for us, PVID has 260 piezometers throughout their whole irrigated area, and every month they go there and take depth to the water table measurements, okay? And that's the data that Saleh put into a GIS and integrated and so forth, and came up then with a groundwater surface, okay, and a depth to the groundwater throughout the whole project, and then averaged all those wells to come up with this graph over the 3 years. So if you read this graph, this is a depth to the groundwater from the surface, okay? So what it's saying that the depth is greatest in January, February, March, okay? And then as the heavy irrigation season kicks in and we have all this deep percolation going on, rises, and the depth to the water table becomes smaller, averaging 2.7 meters here in September. And what we see that in September is where it became minimum in each one of these 3 years. But we're also seeing that as we moved in time, that the depth was getting deeper and deeper in September. Okay? What's going on? Well, Metropolitan Water District, Southern California, okay, who supply water to LA and the big cities in that whole area there, in the LA area, they're paying farmers to leave their fields fallow, okay, so that the water can continue on the Colorado River, be diverted down in the Imperial Dam, and then eventually pumped over to be used in the urban areas along the California coast. Okay? Well, this can be done because the water rights allow you to transfer water from here to there. But in this case, the water rights are still being held by the farmers in the Palo Verde Irrigation District. It's just that they're being paid not to irrigate. Okay? Now they can't do this forever because otherwise they would lose their right to the water. So, you know, this field's going to stay fallow for a couple of years, and I'm going to put it back into alfalfa, then I'm going to leave this field fallow over here, and so forth. And what we saw between year and year is that the fallowed area went from 14,600 acres to about 40,000 acres. Okay, and this is what you see, the end result. Less water is going in to the groundwater. Less water is percolating beyond the root zone into the groundwater system. Just to point out, this 3.3 average depth here is the average depth of the bottom of the open drains in the Palo Verde. So that's where those are the drains that are collecting this excess groundwater and slowly putting it back into the river. So what's happening is the water is not being used it's being the field, it's percolating into the groundwater. Some of it's being transpired and evaporated by the crops. A lot of it's going to the groundwater. The drains are draining that water back into the river system. So it's not lost. It's just being used by the downstream users, okay, which are Imperial Irrigation District and Mexico, okay, and their irrigation systems. Okay. Granted, the quality of this water might be lower than the quality of the water that was diverted in the first place. You have a question? The question was, I'll repeat the question in case, the question was whether water, right, because it's the full amount, because it's going through the whole system, and eventually coming through the groundwater system. And the answer is what is doing is decreasing the diversions as well. Okay, so in other words, they will be diverting slightly less water, so some of the water goes straight through in the river, and some of it is being diverted through the system. So it's a common. So this is just another way of looking at the same data. These are the fluctuations of the groundwater in 2007, where we saw that there was quite a big fluctuation. And this is 2009, which is a much shallower. And we're seeing the direct effects of that foul. Another thing we're working on, but I'm not going into a lot of detail at the time, is we want to establish how the Palo Verde groundwater system is flowing into the river. What is contribution? And what we have plotted here are the groundwater river elevations along the Colorado River, and this is the PVID groundwater elevation along these points here, right close to the river. Okay, and if you subtract this from this, you get a curve like this. And if you do it on a monthly basis, you'll see that many parts of the year the groundwater system is contributing to the river. Okay, and then in the wintertime, the river is contributing water system. Okay, there's some big differences in some certain spots here that we're trying to figure out. But in general, for the 3 years, the ground is contribution to the river in most everywhere along the Palo Verde. This is significant because what the Bureau wants to know is how those phreatophytes, mostly tamarisk, river systems in the west, how much water are those trees consuming? So that was another aspect of this research, which I'll get into in a little second here. Finally, you can compute performance indicators with the water balance and the remote sensing approach, and I'm not going to go into detail. I just wanted to show you, if you plot ET from all those fields, okay, throughout the year, and you divided it by the diverted or applied water, you could see that we get around 60 to 70%, which is the overall efficiency of this Palo Verde irrigation system. Where's the 30% of the water going? Well, we just saw that. It's going into the groundwater, eventually going back over time into the river, and it's spilling straight into the drains and straight into the river. Well, I'll jump ahead here. I wanted to give you a sense of some of the other things that I work on, mainly airborne remote sensing, and I see, for the sake of time, I'm just going to jump ahead here and point out that we are in the same project doing research to estimate the ET of these riparian systems through measurements, through flux towers, eddy covariance and Bowen ratio. And we had towers located in 3 different density of tamarisk so that we could see what differences in ET there were according to density and proximity to the river and groundwater quality. And what we have found that is significant is, if you look at this plot from which is the one that's downwind from salt cedar, and certainly the one that's using more water, that the actual ET of tamarisk is never greater than the reference ET from grass. Okay, so all this fallacy that we hear about people saying that tamarisk use more water than alfalfa, it does a lot of water, but not as much as alfalfa or grass. Now, the problem between, riparian system and the upper Colorado system, you've heard about the beetles that are munching away at the tamarisk, right, a biological form of control. Well, in the lower Colorado is where there is a potential for saving water just because of the wide floodplains with, a lot of extent of tamarisk where just by the sheer acreage, water savings. And this is all very controversial. But I'm going to skip ahead just to get river so we can have a little bit of discussion. Okay? And this is the canal company that's just over the hill here, okay, to the west. That way, okay? It's in the Bear River Basin, okay, and you probably all know the High Uintas is where most of the Bear River water is coming from, about 1,140 millimeters on the average. The Bear River through Wyoming, around Bear Lake in Idaho, and then comes back into Cache Valley and eventually crosses over to Tree Mountain and flows into the Great Salt Lake, okay, down at the tail end. Okay, so the interesting thing, if you do sort of a quick water balance on the river system, how much water vegetation is using, the depletions due to irrigated agriculture, the depletions due to wetland vegetation and reservoir ET and lake ET. The flow into the Great Salt Lake is about 1,200,000 acre feet, okay, of which probably 250,000 acre feet could be available for further use in Utah. So the Bear River is one of the few systems in the West that's unallocated water, okay? But to get hold of that 200 feet, you'd have to build dams and reservoirs to store it, okay? And as thirsty as the Wasatch Front is becoming, it's just a matter of time that they build a dam on the Bear River. Okay, but what I wanted to point out here, this is a very similar. You have a dam, and then you have a out of the dam over. No, I don't think that's immigration. Over where the Bear River goes through the mountains to get over to the other side. I've forgotten there. Yes. Okay, so there's a dam there, right? And the main canal comes right out of there. There's a right-hand side and a left-hand side. And they divert quite a bit of water. Their duty of water, meaning the farmers get 4 acre feet per acre, okay? And their priority is between April 1st and 1st of October. So between 1st of October and April 1st, the water goes to, the water that's flowing in the river is supposed to flow into the Great Salt Lake through the Bear River Bird Refuge, okay? They have the right. Bear River Canal system is behaving very similar to the one in California of the Bear River Canal Company. Okay, that water that's spilling, okay, the water that's going into the groundwater system, that is ending up into the river and being used bird refuge even in the summer months. That okay, which opens another whole can of words if you start talking about improving efficiency. Okay, so keep that in mind because we're going to bring this up in the. Okay, so again, very similar surface irrigation and water, very similar to what we saw on PVID. Most of the crops here are alfalfa, small grains, wheat, pasture. These are not very high-value crops, okay? These farmers get by because most of them have a vertical operation, meaning they have cattle as well, dairy cattle and meat cattle, and they use the maize, the wheat, and the corn, and the alfalfa to feed the livestock. How is this water management? Well, 75%